Let's talk exponential growth and decay. Number one, identify the initial amount A. So there's one thing we're looking for. I guess I don't really have to be that particular because there it is. And the rate of growth R as a percent right there. And there's our percent sign of the exponential function. There it is. And evaluate the function when t equals 5. Okay. And then this is important, round your answer to the nearest tenth. So if you're like, wow, that's a lot of things, let's break it down. And the first thing to break down is, in my opinion, the equations. So if you saw the notes, if you remember the notes, if you didn't see the notes, you don't remember the notes, let's check it out. This is kind of how we looked at an exponential growth and or decay function. And we said that the initial amount is our A. So I'd called it initial value at one point, and I abbreviated it with IV. But the idea is that initial amount, the thing at the very beginning, is what A is. And we determined that that wasn't necessarily the y-intercept just because of the fact that the y-intercept, if things are moved left and right, then that's not the y-intercept, right? And then we have 1.2 down here should be up here, and the idea that we can look at that and say that, oh, okay, well, so then the rate, 1.2, if that's 1 plus r, well, check this out. You subtract 1, and you get 0.2 is our rate, and 0.2 as a percent is 20%, okay? And I guess I could have answered our initial amount was 25 right there, and now we just have to say, okay, what happens when t equals 5? Well, it looks like this. 25 times 1.2 to the 5th power. Now, I'd mentioned, doing this on Desmos. I mean, if you just flat out refuse to do it on Desmos, what you could do is say, okay, well, 1.2 is really 1 2/10, which is 12 tenths, which is 6/5. Okay, so 6/5 to the 5th power. Okay, let me look across the room. 6 to the 5th power. I don't want to do this. I'll just put it this way. It's 1296 times 6. And then 5 to the 5th power is 625 times 5. I mean, that's a little crazy if you ask me. But anyway, that's the kind of the idea. I'm about to grab my calculator. Here I go. And I'll invite you along with me. So 6 to the 6th is 7776, and 5 to the 6th is 15,000. Wait a second. I did 5 to the 6th. How about 5 to the 5th? 3,125. And if we do 7776 divided by 3,125, and then multiply that by 25, we get 62.208. Round that to the nearest tenth, 62.2. I also just realized that I'm using like an old, like you actually punch in buttons calculator. If you were doing it with Desmos and you just like typed this in, it just spits out an answer of 62.204 or whatever it was. So there we go. Identify the initial amount and the growth rate. So same thing as the last one. The initial amount, 1.75. The growth rate is going to be that 0.028. And if I didn't explain it well enough up here, that 0.2 right here, basically how you find that as a percent is you move the decimal 2 places. So boom, it's 20% now. So think about it, 100%, the decimal's here, so you move it, boom, boom, that's 100%. And if you did 1.1, okay, well, you move that 2 places, that's 110%, right? If I did 1.15, okay, move the decimal 2 places, that's 115%. And really the focus is the part after the 1. So maybe I should do it like this. If I did 0.25, that's really, boop, boop, 25%. If I did 389, that is, boop, boop, 38.9%. And then it can get a little trickier. What if it's 0.0023? Well, that is boop, boop, that is 0.23%. You get the idea? So that decimal, each time it moves 2 places. Why? Because percent is literally divide by 100. Yay, and that's what happens when you move the decimal 2 places. Sort of. So let's go back to this one. So 0.028 is really 2.8%, because watch, boop, boop, 2.8%. All right. Now the next part is just plugging in t is 5. So 175 times 1.028 to the 5th. Okay, so I'm not about to do this. I'm not going to do 1 and 28. Let's see, that's 1/10,000th to the 5th power. That's just not going to happen. I'm grabbing my calculator and now. And then just to keep things interesting, if you had done 1.028 to the 5th power, you get 1.1480661, of course. And when you multiply that by 175, and you're going to round that to the nearest 10th, you get 200.9. Fun. Okay, write a function in terms of t that represents the situation. Sales of $10,000, so that's our initial amount, are going to increase by 65% each year. So this is where this equation up here comes into play. We have the initial amount, which is why I already put that in. I did parentheses, and we have all this, okay? So here's what this looks like. They want us to use t, so instead of x, we're going to use t. And increase is pretty obviously a growth type thing, right? And it's going to increase by 65%, which is 0.65. This is where the divided by 100 thing actually comes into place, because it's now we're going that direction, and we get 0.65, right? So check this out. It is going to be 1 plus 0.65. And yes, you can go ahead and simplify that so that your answer over here is 10,000 times 1.65 to the t power. So I did that in pieces right here just to make this point. This whole thing follows the a times b to the x format, right? And the point in mentioning that is if b is between 0 and 1, then that is decay, right? So all that we had to do right here was get it out of this range for it to be growth. It doesn't have to be crazy amounts of growth in order for this to be a growth type thing. Right, a function in terms of t that represents a situation. An item costs $4.50. That is going to be our initial amount, and its price increases by 3.5% each year. So we're going to do 1 plus 3.5% to the t power. And you might think, oh, so it's just it's just 4.5? No. I'm kind of approaching this one slightly differently than I approached that one, just so you can see that here I wrote 0.65 because I'd already converted the percent. Here I've not converted the percent yet, so I need to go boop, boop, and it's going to be 1 plus 0.035. So my answer over here is $4.50 times 1.035 to the t power. And again, that is growth. We are increasing. It just has to not be between 0 and 1. So we definitely are not between 0 and 1 here, okay? Identify the initial amount, A575, the number out front. And let's see. And the rate of decay, R, as a percent. So let's see, it's right here. So it's 1 minus 0.6. We're just going to focus on this part, and we're going to jump it once, twice. This thing is losing 60% of its value each time. One thing that is just interesting enough to show you is that 1 minus 0.6 is 0.4. So it's essentially, if you had 1 and you transformed into 0.4, well, what did you lose? You lost 0.6. That's one thing about percents that might not click right away, but yeah, if I'm at the store and I'm looking at a can of beans, and of course, and it's $1, and they say, oh, hey, it's 80% off. One thing I do is I say, okay, you know what? I'm just going to take that guy and multiply him by 0.2. So that then I'm like, oh, $1 times 0.2, well, that's 20 cents. That's what it would cost. And if you're like, what is going on? Why are we talking about beans and 80% off? It's a percentage thing, because what I could have done is said, oh, okay, well, it's 1 minus 0.8, right, times 1. And this one is this one, by the way. In fact, if it helps, I'll change this to $3 and that to be $3, right? And so check it out. On the inside here, that 1, which is 100% of the product, which we're going to subtract its value by 80%, we're going to end up getting 3 times 0.2, which is what I did right there. Okay. So now evaluate the function when t is 3. 575 0.4 to the third power. 575, that is some ugly writing, Mr. McMath. Let's do better. To the third power. Again, this is 2/5. I can actually do some of this math. So this is 8 125ths. And let's see. If we start dividing by 5, this is now 25. And this is now 115. We could divide by 5 again and get 5. And this is 25, I believe. No, 23. And so we now have 23 times 8 over 5. 23 times 8. That is 4, 2, 16, 184 over 5. 184 over 5. We get 36.8. Identify the initial amount, 475. The rate of decay is 50%. And if you're like, how does he know that? That right there is our rate of decay. They've already simplified it. So if you want to, you can think of it as 1 minus r equals 0.5. How would you solve that? Well, let's subtract r, and we would get negative 0.5. So r must be 0.5. And then, as we hopefully know, you bounce it twice, and it's 50%. Okay. And then now, what does that look like when t equals 3? So let's see. I kind of tortured myself by doing this math up here like this. Let's continue, I guess. 1/2 to the third power, that's 1/8. So 475 divided by 8. 6 times 8 is 48, so let's do 5, 40, 75. That's 959 and 3/8. 59 and 3/8. What is that as a decimal? 3.75. So in the 59.375 and rounded to the nearest tenth, we get 59.4. All right. Identify the initial amount A and the rate of decay, the same stuff. Oh, wait a second. Here, it's right here now. Our initial amount is 1 because there's nothing out front. So that means it's 1. And our rate of decay, just like the last one, if you don't know, 1 minus the rate is equal to 7/8. If we subtract 1 from both sides, we're going to get negative 1/8. So the rate is 1/8. They want that as a percentage. 1/8 is 0.125. So bounce, and we get 12.5%. Now we've got 7/8 to the third power. Well, I can look over at the board that I've written these things down on. 7 to the third power is 343, and 8 to the third power is 512. I'm putting that in the calculator, and I get 0.66992, blah, blah, blah. The nearest tenth is going to be 0.7. So there are your answers there. 1, 12.5%, and 0.7. Write a function in terms of t that represents this situation. A $900 sound system decreases in value by 9% each year. So we start out with $900. It's going to decrease by 9% over t years. And what this is going to look like is 1 minus 0.09. And that's going to look like this. 1 minus 0.09 is 0.91 t. And I'll just point this out. That's our b. So there's a, b, and as well, if b is, I'm sorry, I wrote x. If b is between 0 and 1, we have decay. Well, 0.9 is between 0 and 1, so that's decay. But we're done. It is, that's the answer. I'm not going to rewrite it. There it is. Error analysis. The growth rate of a bacterial culture is 150% each hour. Initially, there are 10 bacteria, so I like that 10 right there goes with that. And then, let's see, 150% each hour. We've got a problem here because it would be like this. It would be 10 times 1 plus 150%. And what 150% looks like is this. It looks like 1.5. So we would get 10 times 2.5 to the t power. That is our problem. It should be 2.5 t. Now we're determining whether the table represents an exponential growth or an exponential decay function, or neither. First thing I like to look at is, are my x's behaving? Are they being weird? Nope, they're going up one at a time. So I like that. And now I'm going to determine, how did I get from here to here? We're sure that it's going to be exponential growth, exponential decay, or neither. So as I look at it, it's minus 4, minus 4, minus 4. Well, so that would be neither. But let me just double check that they didn't do something else, right? So how about this? 32 times, hang on, I wrote an x. 32 times x equals 28. That would give us 28 over 32. And so that is, hey, you could multiply 32 by 7/8 to get 28. But when you multiply, so if this is 7/8, then 28 times 7/8 will give us exactly 24. Well, let's see, 28 times 7/8. We can divide that by 4 to get 2, divide that by 4 to get 7. Well, we would get 49 over 2, which, by the way, is 24.5. So this one is neither. And it's because if this had been 7/8, we could have been onto something. It could have been like, wow, this actually could be minus 4 and times 7/8, which would be really kind of wild. So anyway, neither. Moving on. Same thing. And now I am looking at my x's again. But okay, they're behaving somewhat. They're timesing by 5. I'm sorry, they're increasing by 5. But really, I'm most concerned with this. So 2 times something gives you 8. Well, we know that's 4. So, yeah, times 4 times 4. Let's see, is that times 4 as well? I think it is. So, yeah, times 4 times 4. Okay, so this seems to be a growth function. That's nice. Determine whether it's growth or decay, and then identify the percent. This is definitely growth, because that is outside of our 0, 1. It's greater than 1. And our rate of change is just going to be 10%, because, as we've said, 1 plus r, 1 minus r equals 1.1. So if we subtract 1, we would get r equals 0.1, and boop, boop, that's 10%. Next. Same thing, is it growth, is it decay, and find the rate of change. This is also growth. You might go, well, hang on a second, what about that 0.4? That just means our initial amount, our initial value is 0.4, but this is still growth. And looking at that, our rate of change is 6%, because 1 plus what amount is going to give us 1.06? Well, 0.06, and we bounce to get 6%. Same thing. This one is decay. How do I know it's decay? Well, because that's between 0 and 1. 4/5 is equal to 0.8. And so what is our rate of change? It's going to be 20%. How do I know? Because 1 minus our rate is equal to 0.8 or 4/5, however you want to look at it. If I subtract 1, I get 0.2. And in this situation, it actually doesn't really matter if we call this positive or negative, because it is the rate of change was 20. And we could say, yes, we are losing 20%, but you're not going to call it positive or negative on that one. Rewrite this in the form of this or this to determine whether it represents growth or decay. Well, let's be honest. 1.06 is going to be growth, so let's get our rewrite on. What we're going to do is 2 times 1 plus 0.06 to the 9t power. And how we can rewrite that so that we just have a regular old t right there is we can kind of distribute this 9 power. So you get 2, and then this is here, let me go and write the 1 plus 0.06 9th power. And you know what, I guess I didn't even have to do it that way. I could have done it like this. 2 times 1.06 to the 9th power with t out there. And then I'm definitely going to grab a calculator. 1.06 to the 9th power is 1.68947, blah, 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 blah. And so it says round A and R to the nearest hundredth if necessary. Well, A, nothing was happening to A, right? But R definitely got changed. So I guess in this situation, I was about to say, I guess this was the right way to go. However, we're going to be able to pretty easily figure out what R is without it. So 2 times, and I told you it was 1.689, blah, blah, blah. So let's just round it to to the nearest hundredth, 1.69 to the t power. So this is your answer right here. It is growth. And let's go to the next one. Rewrite this one in the form of all of that stuff to determine if it's growth or decay. Again, I think it's growth, but let's go ahead and figure this out. So we got 0.4 times 1.16. Now, how is this going to work? Well, you subtract exponents when you are dividing. So it looks like this. And notice I did not write an exponent here because it would be a 1. And ones, as exponents are invisible. I mean, because there's a 1 there too, right? But we just don't usually write that. Oh no, I got rid of so much writing. There it is. And at this point, now we really can talk about our A changing, because what we have is 0.4 over 1.16 times 1.16 to the t power. So again, I'm going to grab a calculator. 0.4 divided by 1.16 is 10/29ths. So here, we could say it is 10/29ths times 1.16 to the t power. Or we could say it is, if we're doing to the nearest hundredth, 0.34 times 1.16 to the t power. What's the difference between these two? Well, this one is 100% accurate because we didn't round, and then this one is rounded. I wouldn't really worry about it. I think they've kind of mentioned, rounding. So go with a rounded one, no big deal. Choose a graph of an exponential function that has the given characteristics. Y-intercept of 3. No. Yes. Yes. And an asymptote is the x-axis, which would be this guy. So no again, and no again, and yes again, and yes again. If you're not sure what an asymptote is, it's the line that it's this line, and it's that this function is approaching but never touches. Same thing here, and if you're like, but it's not approaching, it's going away, it's still technically approaching it when you go that direction. And then last but not least is decreasing over its entire domain. We haven't talked about increasing and decreasing for a while, but decreasing is when you're in the, this is supposed to be a roller coaster, and as you go along the function, as it increases, as the function is increasing, you are decreasing. So it is this one right here, not this one, because this one would be increasing. So this would be increasing, whereas the other one is decreasing. Got it, got it. Write a function that represents the balance y in dollars. Well, there it is, y in dollars after t years. You got $1,400, $1,400 initially. That earns, so that's 1 plus 10%, annual interest compounded semi-annually. Well, we need to go back and talk about something. If we go back, what I mean is back here, this is great if we are compounding once a year. So what does that mean? Well, here, let's take $1,000. Let's take $100. No, we can do 1,000. And let's run it through two different scenarios. So let's do what we call semi-annually. And let's go with annually. Okay, so this one over here is only going to compound. So year zero. So there's our year category, and this will be our account. So we put $1,000 in there, and the year goes by and nothing happens. 1 year goes by, it's gone up 10%. So now we have $110. Okay, well now going over here, we have the amount of 6 months that have gone by, so to speak. And here's our account. So 1 6 months goes by, and yeah, we have, hold up, let's back up. So at 0 6 months, we have $1,000. At 1 6 months, we've got 110 like that, or 1,100 like that, just like the other account, right? So now let's say a second year goes by. So adding 10% means we're going to add another $110. So we got 1,210. But over here, a second 6 months has gone by, and now we're at 1,210. So check this out. This was 1 year. Okay, and over here, this is 1 year. And now do you see the like, oh, I see over here, this is more money, right? Maybe you don't see it. Let's do a couple more rounds of this. Okay, so let's do a third 6 months. And so now we're adding $121. So 121 is like that. And then a fourth 6 months goes by. So let's see, now we're going to add $133. So 146, 1464, like that. Well, okay, now this has been 2 years. Well, notice over here, this is 2 years. So this is the same as this. You're definitely, do you see the difference now? Like I didn't even do anything over here because this is the same timetable as this, all right? So let's stop there and go back up here and talk about this. Maybe you like paid attention well enough during the notes that you're like, yeah, I get it. So here we go. There's which could be account, which could be amount. it could be like, what you end, here's like in English, it's what you end up with. So like here, let me separate these out so you can just kind of see the thoughts spread out. It could be them setting up the problem as like, hey, after 10 years, you have $1 million. Well, that's how much you ended up with, right? And that would go here. So the account is equal to P. What the heck is P? It is the principal amount, which is our initial value, which is our initial amount, right? It's not necessarily the y-intercept, especially, if we're doing stuff with other things, right? So anyway, there is A equals P times 1 plus, now this should be familiar, we've been doing this part, plus R, the rate. Yeah, that's what we've been doing, but hold up. It's going to be divided by N. What the heck is the N? This is the number of times it compounds. So if it's annually, in fact, let's write this out. So annually would just equal 1. And then it would look like this. A equals P, 1 plus R to the T. Because there's an invisible one right there. And then there's an invisible one right there. This yellow one is a common one that we'll use. And then if it happens semi-annually, well then basically, so semi-annually like this one, N equals 2. For semi-annual, it happens twice a year. You could do quarterly, where N would equal 4. You could do it monthly. I hope you kind of get this idea, where N would equal 12. You could do it daily, where N would equal 365. And someday we will talk about constantly, but not today. So N is the number of times it compounds. That N actually shows up right here as well. So why don't we do this? R, I didn't write what R was because we already talked about R, but R is the rate. And then last but not least is T. T, I hope you know, stands for time. And time is going to be in years in this situation. I guess you could probably say it's going to be in all situations, all right? And that was in our notes. If you didn't see that, oops. Now you've at least been caught up here. So let's back up. Write a function that represents the balance semi-annually. So we have y equals 1,400 times 1 plus 0.1, that's our 10%, over 2 to the 2t power. Now I'm going to simplify this a little bit, really just simplify this internal part right here. 1,400 equals, let's see, 0.1 divided by 2 would be, well, here, I'll write it out to the side, divided by 2, that would be 0.05, right? And 1 plus 0.05 is just 1.05 to the 2t power. Now, you might think, well, okay, so are we done? Yes, we're done. I'm not going to mess with the 2t here. We did that in other ones. Where did we do that? Where we rewrote some things. Was it here where we rewrote? Yeah, we were rewriting some things here, right? It was somewhere that we rewrote some of these. Here it was. Here we rewrote it. And you know, I don't 100% know the reason why we had to rewrite these versus on this one. So don't worry about it too much. This is our answer. If I had to guess, I would say it's because this communicates that we are doing a compounding interest type problem, and this is the type of answer that you would see, and it would communicate, this 2 means that it's compounding twice. So there we go. Let's move on. 19, modeling real life. You deposit $9,000 in a savings account. So here, let's start writing this thing. $9,000. that earns 3.6% interest, annual interest compounded monthly, so over 12, and there's that 12, to the t power like that. So this is in your savings account. So savings account right here. Yeah, because this says write a function S that represents the balance in dollars of your savings account after t years. Now, we're going to go ahead and simplify that internal part again, like we did on the last one. So 9,000 times, let's see, I'm going to zoom out just so I can do some thinking. Divide that by 12. Oops, it is not 3.6. It is 0.036. And when we divide that, we are going to get 0.003. Okay, so then what we can do here is 1.003 to the 12t power like that. So that's our first answer. And then now it says write a function, let's switch colors here, write a function B that represents the amount saved after t years. Well, what that means is if we were just talking about savings, they would have said S of t. So why are they saying B of t? It's kind of like they're saying big B stands for the bank. And there was this other scenario, you save $40 a month in your checking account, right? So $40 a month is just going to be, 40 times 12 months times however many years that you're talking about it, right? It's just multiply. It is not exponents. So writing a function, it literally is just that with a plus sign in between them. So I'll write this out, 9,000, 1.003, 12t plus 40 times 12 times t. That is that. And now find b of 3. So all we're going to do is take a 3 and plug it in there. And there, we're going to plug in a 3. And I'm going to grab a calculator to do that. And just for fun, I'm going to pause and give you that this part right here, this part after 3 years is, let's see, $10,024.81. It's actually 800. Oh, hold up. It's actually, if we're going to get nitty gritty here, it's that exactly. And then the other part is 40 times 12. 40 times 12 times 3 is 1440. So plus 1440. And does it tell us what we should round to? It doesn't. So here's what I'm going to do. I'm going to round this to just 1 cent and get rid of that and add a 1440. So we're going to get 46411 and 81 cents. $11,464.81 is our answer. Okay, that's the end of it. Let me know what questions you got about exponential growth and decay. See ya.